Hello guys, today we'll take up a very important topic which is molecular orbital representation of carbon monoxide. Well, most of the students find it a very vexing topic and therefore I decided to make a video on it. So without further ado, let's get started. The first important thing to do is writing the electronic configuration of various atoms involved, and carbon with an atomic number of 6 has an electronic configuration of 1s2, 2s2, 2p2, while oxygen with an atomic number of 8 has an electronic configuration of 1s2, 2s2, 2p4. So this is the first important thing to do, that is writing the electronic configurations of various atoms involved. So carbon 6 has a configuration of 1s2, 2s2, 2p2, and oxygen 1s2, 2s2, 2p4. Now, after this, we need to realize that in molecular orbital representation, the inner shells are not involved. So we can completely ignore 1s2 of these two atoms, since 2 is the valence shell, so the electrons in the first shell, they can be completely ignored. And therefore, now we are in a position to show the representation. So the representation consists of a vertical axis where we will show energy, and we'll use black to represent the orbitals of carbon atom. So the black shade, so we can show 2s orbital of carbon in this particular fashion, and we will use blue shade to represent the corresponding orbitals of oxygen. So this is the 2s orbital of oxygen, and since oxygen has greater atomic number, therefore its orbital is at lower energy compared to the corresponding orbital of carbon atom. Okay, so this is the 2s of carbon atom and this is the 2s of oxygen atom with its energy significantly lower. Now similarly, the 2p orbitals of carbon, we can represent them in this particular fashion. So these are the three 2p orbitals of carbon, that is 2px, 2py, 2pz, and simultaneously we have the corresponding orbitals of oxygen, so we can show them in this fashion. So these are the three 2p orbitals of oxygen atom. Okay, and after this we'll just show the electrons. We have 2 electrons over here, we have 2 electrons here, we have 2 electrons, and here we have 4 electrons. So now we have shown the electrons present in all of these orbitals. Now let us see which all orbitals start to interact. So first of all, the energies of these two 2s orbitals are quite similar, and therefore they start to interact, and the result is formation of a completely new set of orbitals which are called molecular orbitals. And if 2 orbitals interact, then exactly 2 molecular orbitals form, half of which are bonding and the other half is anti-bonding. So in this particular case, it indicates that we are going to get one bonding molecular orbital, and for the bonding we'll use the green shade. So this bonding we can represent as sigma 2s, and simultaneously we'll get an anti-bonding orbital which will represent using the red shade, and let's say this is now sigma star 2s. Okay, so the green represent the bonding orbitals, molecular orbitals, while red will represent the anti-bonding molecular orbitals. Another important thing to note is that the energy of bonding molecular orbital, it is lower than the energy of the participating orbital having least energy. So you can see that the bonding molecular orbital's energy is lesser than the oxygen's 2s orbital. Okay, and similarly the anti-bonding molecular orbital's energy is greater than the highest participating orbital's energy. So here 2s of carbon has higher energy among these two, between these two, and this particular anti-bonding orbital has more energy. So this thing has to be noted. And thereafter, now a special case comes. Since the 2p orbitals of oxygen are significantly lower in energy, okay, compared to the carbon's 2p orbitals, we have the case in which now the 2s orbital of carbon and the 2p orbitals of oxygen have similar energies, and therefore it makes it possible for this 2s and 2p interactions also to happen. Okay, which was usually not the case with homoatomic molecules such as N2, O2, F2, etc. But in this particular case, it becomes possible because this 2p is having significantly lower energy compared to carbon's 2p, and it is having similar energy as these 2s orbitals. Now, we are all aware that the 2p orbitals are mutually perpendicular. So they are somewhat like this, placed in space. So we can show them in this particular fashion in space. So they are mutually perpendicular. These three are the 2p orbitals. Okay, and these 2p orbitals are going to interact with the 2s orbital. Now 2s orbital is spherical, and this particular spherical orbital can interact only with one of these orbitals. It cannot interact with all the three simultaneously. Okay, so if this is the perpendicular set of orbitals, either you can have interaction with this, or you can have interaction with this, or you can have interaction with this, of this particular spherical 2s orbital. And therefore we note that this 2s orbital can interact only with one of these 2p orbitals, and let's say this is 2pz orbital. So assuming that this 2s interacts with 2pz orbital, now once again we are going to get a bonding orbital and an anti-bonding orbital. So the bonding orbital will have lower energy compared to the participating orbital having least energy. So therefore the bonding orbital can be shown over here in this particular fashion. We can write it as sigma 2s 2pz. Okay, so which clearly shows that which orbitals have interacted. The 2s and the 2pz orbitals here, they have interacted, and this is the bonding orbital. Similarly, the anti-bonding orbital from this interaction will have more energy than the energy of highest participating orbital, and therefore the anti-bonding orbital would be somewhere here, and this will be represented as sigma star 2s and 2pz. So star and the red color shows basically the anti-bonding orbitals. So this is a special set, the 2s interaction and the 2pz interaction that has created a bonding molecular orbital and an anti-bonding molecular orbital. Now we'll come to the usual interactions which will happen between the set of 2p orbitals of carbon and the set of 2p orbitals of oxygen. And you will have interactions in this fashion: 2px with 2px, 2py with 2py, and 2pz with 2pz. And therefore we are going to get a total of 6 molecular orbitals, out of which 3 are going to be bonding and the other 3 are going to be anti-bonding. So once again we'll stick to the color code, and our bonding orbitals would be like this. We'll have 3 of these bonding orbitals, 1, 2 and 3, and all of these will be at a lower energy than these 2p orbitals, the participating ones, and this would be sigma 2pz, this is pi 2px, this is pi 2py, and the anti-bonding orbitals we can show over here, and these will be in this fashion. Okay, and this will be sigma star 2pz, this is pi star 2px, and this is pi star 2py. So this completes now the entire set of molecular orbitals, so which I am going to quickly summarize. So first of all, we had interactions between the 2s of carbon and the 2s of oxygen, which resulted in a bonding sigma 2s and an anti-bonding sigma star 2s. Then we had interaction between the 2s of carbon and the 2pz of oxygen, which resulted in bonding sigma 2s 2pz and sigma star 2s 2pz, the anti-bonding one. And finally we had the regular interactions between 2p set of carbon and the 2p set of oxygen, and that resulted in 6 molecular orbitals, out of which 3 are bonding and the other 3 are anti-bonding. The bonding molecular orbitals energy, each one of them will have lower energy compared to the energy of least participating energy orbital, and over here the anti-bonding will have correspondingly more energy. Now the special thing which one must take a note of it before we start to fill up the electrons is that the energy of this anti-bonding and the energy of this bonding orbital, it is very very close, and the essence of their energies being close to each other is the fact that now these orbitals cannot be used for filling up of electrons. So we can basically completely ignore these two molecular orbitals. So their energies are too close. So essentially, in a way, they destroy each other. So this bonding molecular orbital and this anti-bonding molecular orbital, they essentially destroy each other, and we don't need to bother about them. So therefore, now let's start to fill up the various electrons following Aufbau rule and Hund's rule. Okay. So here we have 4 electrons. So using the Aufbau rule, first of all, we'll have now 2 electrons entering this orbital. Then the next 2 electrons will enter this bonding molecular orbital. Now here we don't need to bother. And herein we have now 2 plus 4, 6 electrons. So 1, 2 following Hund's rule, 3, 4 and finally 5 and 6. So therefore we see that 2 electrons have entered anti-bonding orbital, that is sigma star 2s 2pz, while the rest others have entered bonding molecular orbitals, and we can see that we have 2 plus 2 4 plus 2 6 plus 2 8. So basically our figure for bonding electrons is 8, and the number of anti-bonding electrons which are present in sigma star 2s 2pz, that is simply equal to 2. Therefore bond order is equal to half of number of bonding electrons, number of anti-bonding electrons, and that boils down to 8 minus 2 divided by 2, and which is nothing but 3. Therefore we conclude that the bond order in carbon monoxide molecule is 3. Now comes the next interesting step, which is finding the bond order in CO+. So CO+, which is basically carbon monoxide whose one electron has been pulled out, and in order to obtain CO+, we first need to remove an electron from CO, and this can be done by removing the electron from the highest occupied molecular orbital. So this is the highest occupied molecular orbital, and therefore we will remove an electron from it. And when we remove an electron from it, we observe that there is no change in the number of bonding electrons. There are still 8 as the case previously, 2, 2, 2 plus 2. And however, the number of anti-bonding electrons, because we have pulled out one electron, so the number of anti-bonding electrons has reduced by 1 and is just equal to 1 now. Therefore, the bond order will be equal to half Nb minus Na, and that is equal to half 8 minus 1, and that boils down to 3.5. So the bond order in carbon monoxide increases by half a unit once the electron is removed. So I hope this explains to you very well how to draw the molecular orbital diagrams even for heteroatomic molecules, and go for the representation in this particular smooth fashion. So I hope this particular lecture will be really useful to you. Please feel free to post your comments and your doubts or queries. Thank you so much.